Good morning, everyone. Welcome to the EasyPower Tuesday Refresher. This is Jim Chastain, and I appreciate everyone joining us this morning for a discussion about arc flash involving bus ducts. As we are wont to do, we like to start off with a poll and get a little bit of feedback from the audience at the same time. And so today our poll questions are going to include how frequently you use bus ducts in your studies, and then a request for feedback on future webinar topics. So let's go ahead and launch the first poll question. Appreciate your participation and some feedback. And as I mentioned before, the feedback has more to do with making sure that we're covering the topics requested, and in some cases steering the topics, the discussion as we're proceeding. Appreciate your feedback and your attendance today. Here's how the audience shapes up today, and that makes a fair amount of sense. So let's move on to the second topic, and it's more some feedback on how we can provide information that's useful to the audience going forward. And so if you would, let us know where you would like topics covered. And by all means, participate in the discussion today through the questions list. And certainly after the fact, if you have individual questions, you're welcome to contact tech support at easypower.com or send us an email, and we can provide and collect feedback that way. And here's how request shapes up there. Protective coordination is usually a fairly highly requested subject. So again, appreciate everyone for participating, and let's move on to the discussion this morning. So apparently a lot of people have exposure to bus duct modeling and systems that require bus duct protection. And so what we expect to do today is to cover some of the considerations that you should be taking into account as you're both collecting data and conducting the study. They are instruments for power system distribution of electrical power that are fairly pervasive. You can see them both in commercial and in industrial installations. And in general, the bus ducts are assembled or manufactured in predetermined sizes that are assembled on site. The lengths are fixed, and the tools or the bus ducts permit variable equipment drops to be moved around, which gives a lot more flexibility to a plant's configuration rather than having to recable either temporarily or almost impossible with permanent cabling when loads need to be moved around. The problem is seldom are protective devices distributed along the bus ducts, and it's this length that affects the instant energy. And that ends up being generally the issue that we need to address when we're doing the modeling. So the technique is relatively easy when you think about it. Basically, you determine the overall length of the bus duct that you're trying to model, and then break it up into average lengths. And so this decision and the granularity involved depends a lot on you as the system modeler or analyzer, what makes sense in terms of the energies involved and the loads involved and some of the distances from the equipment that people are operating to the bus duct itself. And so the total bus load represents local drops at each length. So we're grouping, effectively lumping the loads averaged at these, located at these average lengths. And so I'll talk more about that. It's easier, I think, when you see the example. The instant energy at the bus drop connection will increase, and that's where the real hazard is. And it's nice to see with the EasyPower tools effectively what that means. So let's take a typical installation. So we're talking about a 480 volt system, and just for hypothetical purposes, this particular building has a single bus duct run that's 500 feet long and a 1600 amp capacity. And so just for this illustration, we're using 100 feet average bus lengths as my bus parameter. And what we're going to do is at each connecting bus, we're going to lump the loads, and anything that's within 50 feet, either upstream or downstream of that bus, will be included in the total loads for that drop. Now, as we talk about that, you can see that if you have very large loads, it may make more sense to have smaller average bus lengths, and that you need to take into account as you're considering how to model the system. So each drop in this case will have an individual fuse, and the main protective device on the incoming to the bus itself is going to be 1600 amps to cover the total capacity. So let's see what the EasyPower model looks like. All right, so what I've done here is we have a low voltage power circuit breaker as my incoming switchgear, and then I have an individual fuse going to the bus duct itself. And so in this case, we selected a generic 1600 amp copper bus duct, and this is modeled from in the EasyPower equipment palette by utilizing, in fact, let me just kind of redraw this from scratch here. So it's this icon on the, in my case, the second row is called busway, and I've installed one, and I'm going to the first bus, and then I'm going to connect a busway to the second bus, and it's going to be the same characteristics. As I open up the busway data dialog box, you can see that we've selected a generic manufacturer, standard type. We're using 100 length ampacity of 1600 amps, and it's copper, and from that we calculate the average impedances. Well, I'm going to use this as my average, if you will, bus duct length. So I'm going to copy and paste this into the second bus that I've installed. Since I have 5 connections, I'm going to copy this second part, hold down Control and select both of these items. Now do a Control C, and then a Control V allows me to paste this over here and then reuse this length connection as we go along. So I'm going to do it again until I get the 500 feet that I was looking for. So there's 1, 2, 3, 4, 5. Now, as I indicated earlier, the problem is that for this total length, the only protective device we have is this, in this case, the main fuse that we selected. So if I have a load connecting at this cylinder, at this butt, at the end bus, then it's going to be protected by this fuse. And it was, as we've seen even in the most simple examples, the instant energy will increase as we go through this leg, or we go through this bus duct. So let's see if we can, I guess since I've already indicated the capacity we've copied from the first bus, I can go ahead and fault the bus and look at the current. And what we see is that the current, if we look at this a little closer, the current will stay, essentially, because of the impedance, will drop at each bus. So here it's 42,000 amps, 37,000 amps, 33,000 amps, etc. Now again, the counterintuitive nature of arc flash is at work here. So our first thought is, well, if this is lower current, then we may have lower energy, but as we go and calculate the instant energy, what we see is that that energy actually increases along the way. So where we start off with our first bus at 5.6 calories, the last bus down here ends up at 21 calories. And this is real, and the problem again is, if we look at our range for arc flash, the problem is the trip time, because we're depending on that primary fuse, will increase to the point that we have a very elevated instant energy. So the problem turns out less with the loads. In fact, let's start putting some loads in here and kind of show where that leaves us. The problem is actually with the bus duct distribution itself. All right, so I'm going to just activate this load, a typical load, and just throwing some large numbers on there. But because our drop then will be fused or protected for that particular section, now I can go in and, in spite of having a high instant energy up here, my protective device will give me a respectable instant energy calculation when I look down at the load that we're working on. So if we look at what's going on there, we're seeing we have a 1 calorie instant energy because it's being protected by that upstream fuse. So if we go back and look at how this results in the overall scheme of things, let's go ahead and put a load down here at the end. So the question becomes how, if I'm lumping the loads, and let's kind of, I've created a subsystem here that gives me a bus duct load. And so we're just going to drop it on this last bus. All right, so this is a fairly hefty load, and it represents the lumped sum of all the loads within the last 50 feet. Whereas this particular lump total will be the total 100 feet here and 50 feet downstream. So consequently, at each bus, we're lumping the loads within 50 feet of that bus, with the exception of the very first link here. So now that I've done that, and because if we're considering this as a lumped load, what do we put in as the protective device? Well, certainly if we're adding up all the current, then potentially there's some argument to be made that we should add up the total current that could flow through the protective devices. But what that gives us is an artificial number when it comes to calculate instant energy. So the fact is, even though we're averaging the lumps out here, the possibility of a fault at any individual load is much greater than it would be on the whole total. And so again, as the person doing the analysis, the size of this particular protective device, and when I'm thinking about worst case, isn't going to be the sum of the total. It'll be actually the largest one that's coming off of this particular drop. And again, what we effectively are doing, and when you think about it, the instant energy in terms of an individual load is dependent upon, let's go back to short circuit, is dependent upon the fault that's going to happen at that particular load. And so what we're doing here is faulting a specific bus, and the current that's involved has less to do with the location on the bus duct and more to do with the total that we've included as far as the load. So it actually increases the total current that this bus is going to see, but it really doesn't do anything in terms of the instant energy at this particular point if we have our protective device sized for an individual load. So the point I'm trying to make, and this is a decision you need to make as you're doing data collection, as you're looking at the analysis, in terms of the overall contribution to the place where the most hazard exists, which will be at the drop for the bus duct, lumping the loads is a pretty good approximation. But in terms of the downstream protection, this can, like I say, an argument could be made for either summing all in parallel or just sizing this for the worst case, which would be the largest device, which again give us the largest amount of let-through energy. So when we come back and fault the bus, let's just fault the single bus. Look at our arc flash and the incident energy there. It ends up still being a fairly reasonable number, even though when we look at the whole system, we're getting some very elevated energies at the bus duct itself. So the problem ends up being, and the way I modeled this is I drop a cable from my bus drop, and then if I want to, I could put individual disconnects at the loads depending upon how the physical setup is for my system. And in either case, as long as what do I want to put here? I want to put a breaker. In this case, I'm using a 600 frame and a 300 amp molded case circuit breaker. I still have very good protection as far as operator safety at the loads, but I need to really caution folks about exercising any switchgear up here that's next to the hazard, next to the bus duct itself. Okay, I feel like I kind of stumbled through that, but so the technique is this. I come up with a scenario where I can break my total bus duct up into average segments. And what I chose in this case was 100-foot segments, and then I lump the loads that are within 50 feet, and I use that as my load for each of these virtual drops. And then that gives me a reasonable assumption in terms of the fault contribution at each of these bus drops on the bus itself. And as far as a downstream, I'm using the largest load, which would have the largest protective device at each of the drops on my virtual bus to give me the loading that's going to be downstream. So that's what I would label the equipment, and then I'd have, again, much higher energies calculated and basically don't work on the bus duct while it's hot. Okay, so I'm thinking I stumped all over that one. Let's see where else we are. Now, the same thing can be seen when we look at even a 240 volt bus, and the significance here, as it is in a real plant, as we move or change loading at each drop, say we move the drops around, as long as it stays within that same 50-foot vicinity, radius from the virtual bus, we don't have to change the main bus. All we're going to do is change the loading at each of the drops that we've set up. So it's relatively minor change in terms of the calculations in EasyPower, and frankly, it won't change the system loading because that's all dependent, as far as labeling, that's dependent upon the protective device that's localized either for that load or coming off the drop. To show that in lower voltage system, here's a situation where that's exactly the case. And here you can see we've come up with a 42-foot average length that we're using for each of the segments, and then when we've lumped the loads, in this case these were relatively small loads, and we can model them either as individual, in this case a motor, individual motor, there you go, or as a group of motors like we would in an MCC. And so the same discussion applies as to, okay, if we've done a group modeling, what are we going to use for the protective device? And in that case, at least I would argue or suggest I want to use the largest single breaker because that would have the greatest amount of let through to give me the calculations for downstream energy. And if we go to look at our current, we can say the same thing. Whoops. I just want to look at this series of energies along the bus duct. Okay, so the bus originates here from these two center points, and you can see we have a decreasing current as we go down the bus duct. On this side it's 69 and then 67. Over here it's 72 and 7,000. And as we calculate incident energies, we can see that it actually goes up, although this is much more civil in terms of what the initial energy is because of the shorter length of the bus. But you can see it starts at 1.2 calories and goes to 1.5, and over here it starts at 0.7 and ends up at 0.8. And this is all based upon the fact that we have the initial current is protected from the same upstream fuse, and that the load energies will be a factor of the localized protective device. And so it'll be, again, a fraction of whatever is going on at the busway. Okay, so that pretty much is the technique and the different things you need to take into consideration. I think most of this discussion would be included in assumptions that you make for the study. So yes, that's what this example is. K is specifically a 240. You're asking me where it came from. This actually just came from a client's file, a customer's file that's sent in for assistance in modeling. And so it can be done pretty much straightforward in the EasyPower modeling. All right, that pretty much covers what I wanted to say. I wanted to check to see if there's any questions. I appreciate everyone attending today and the feedback on the polls and the survey. And I invite you all to check the website for updated schedules and new announcements on webinars. And we look forward to talking to you in the future. Thank you one and all.